A problem that we will frequently encounter in electrostatics is to calculate the electric field in the vicinity of a charged object where that object is not at all like the point charges we have considered before. Here we look at the specific example of a rod carrying a total charge Q, which is uniformly distributed along its length, and we want to calculate the electric field at point A. The first thing to note is that if the charge is uniformly distributed along the length of the rod, we can define a quantity called the charge per unit length, here given by the Greek symbol lambda, that is constant everywhere on the rod. Now, in order to evaluate the electric field at point A, we will break up the rod into a number of tiny little segments. If we choose our segments to be small enough, we can approximate these as point charges. So, for example, if I choose a tiny little segment of the rod with the width dx, I can calculate the electric field that it will produce at point A from the expression for the electric field of a point charge. Here we use the notation dE for the electric field to emphasize that this is a very small electric field produced by the tiny amount of charge dQ that resides in the element dx. To calculate the total electric field at point A, we can now divide the rod into a number of similar little elements and calculate the small electric field produced by each of these elements at point A, and then simply add together the little electric field vectors produced by each segment to give us the resultant electric field at point A. Therefore, the electric field at point A becomes the sum of a number of tiny little electric field contributions. And if we want our calculation to be exact, we need to add together essentially an infinite number of tiny little electric field contributions. However, we know an infinite sum is just equals to a definite integral. So in this case, to calculate the total electric field at point E, we must calculate the integral of our electric field expression evaluated over the entire length of the rod. We can write this in a slightly simpler way by noting that the amount of charge that resides in each of our elements, dQ, can be written as the product of the charge per unit length, lambda, times dx, where dx is just the tiny little length of each element. Now, this integral is still not easy to solve because both the direction of the electric field produced by each little tiny segment and the distance away from the point where we want to calculate the electric field depend on x. If we look at our rod, this basically means if I move the position of the element, so if we change the value of x, we change the distance between our element and the point where we want to calculate the electric field, and we change the direction here given by the unit vector r hat pointing from the particular element on the rod towards point A. So in order to calculate this integral, we must come up with a solution. And this solution is to write the distance r as a function of x and to calculate the x and y components of the electric field at point A separately. First, let's write r as a function of x. So we start with the tiny electric field produced by a tiny little element of width dx at point A. We know that irrespective of where we choose this element to be, that its distance away from point A can be determined by Pythagoras' rule. So r squared we can write as just x squared plus a squared, where a is the distance from the end of the rod to our point where we want to calculate the electric field. We can substitute this into our expression to get the expression shown on the slide. Now we want to calculate the x component of our electric field, but the expression that's shown on the screen is still a vector dE. Now if we note that r hat is just a unit vector, its x component is given by the cosine of theta, where theta is the angle shown in the diagram. So we can write the x component of the field produced at A by a tiny little element with width dx as the expression shown on the screen. We can simplify this further by noting that the cosine of the angle theta is defined as the distance x divided by r. So by substituting all of this into our expression for the electric field, we end up with an expression for the x component of the electric field produced by a tiny little element of width dx somewhere on the rod. In order to calculate the total x component of the electric field, we now have to integrate this expression from x equals 0 to x equals L. So we need to evaluate the definite integral shown at the bottom of the screen. Now, by the standard pattern that results from the chain rule in mathematics, the solution of this integral is rather simple and shown here at the bottom of the screen. Now, see if you can follow this argument by calculating the y component of the electric field on your own. See if you can find the expression shown here at the bottom for the y component of the electric field, given the solution to the integral that appears on the screen.